Hey gang, hope everything's going well with you. Welcome back to Biostat. We are going to discuss tests that are specific to categorical data. We've actually already discussed one. When we did the one prop Z test and one prop Z interval, that was technically for categorical data. We were talking about proportions. The very nature of what defines the proportion is a category. Like you fit into a specific category out of a number of people or items that we've chosen. And so those represent categories. So today we'll talk a little bit more about that, but we'll go into some further types of tests that we can do with categorical data. And I'm going to do some of these examples by hand in the next couple of sections, but we'll do most of the things in R. But just bear with me while we go through the by hand things. I do this because I want you to really appreciate the by hand method is nice, and I want you to appreciate the math in that, but I also want you to see why we appreciate our technology so much as well. I think that's very important. So let's talk about categorical data again, kind of refresh our memories. So basically categorical data is data that can be placed into groups or categories. All right, so that's kind of what it goes with. We sometimes call this qualitative data. All right. So we're really talking about wordy descriptions of things, and we get counts from those things, right? So examples of categorical data might be if you take 1,000 people, how many of them were male, how many of them were female, as far as your gender was concerned, or your sex. The species of an animal, maybe a bird species. You have certain bird species you're interested in. Each one of those, you know, if you go out bird or insect collecting, you might have different species that you keep count of. All right. Age groups can also be considered categorical because you can have age ranges like folks that you have in your out of 1,000 that were younger than 20, those that were between 20 and 24, 25 to 29, and so forth and so on. So there's a lot of different ways we can categorize data. All right. Categorical data, that is. So basically, any category where we can get a count of something is considered categorical, if you think about it that way. All right. We can use these counts in our categories to form proportions. All right, which is what I was kind of talking about before. And like I said, we did the one prop Z test and one prop confidence interval as well for proportions already. And that was kind of a precursor to what we're doing today. And so proportions based off of that can be treated like the distributions we've seen of sorts. That's why we can use the Z distribution when we talk about how proportions are laid out. But we can also use the chi-square distribution when we talk about proportions as well. I'm not going to get into depth into why we can do those things here, as I don't think it's necessarily glaringly important for this course. All right. So let's get right into the two sample interval and the test for proportions. Let's get that short up. So the assumptions that we usually have for every test or whatnot, or confidence interval, these are pretty much similar to what we've seen before, except for now we're dealing with two samples rather than just one sample. So there are two simple random samples. That's the first assumption we have here, that are independent of one another, so they can't be from the same sample. They have to be two separate samples, right? So you get a proportion from each one. Each population for each sample has to be at least 20 times as large as the sample drawn from it. Okay. The individuals in each sample are divided into two categories. So this kind of brings back in that mindset of a binomial situation. Either the people in sample 1 met your criteria of what you're interested in. Maybe you're interested in, I don't know, I'm trying to think of something good here. Let's just use voters, for example, because it's easy to do. The percentage of people who voted Democrat out of a group of 1,000 in one sample, and then you've got another one that you're interested in how many people voted in that group that were Democrat as well. So you get proportions. So you got Democrat or not Democrat, or whatever you're interested in looking at. So basically you can have to be able to divide those groups up into two. into two separation, being able to be separated into two little subcategories, if you will. Both samples, this last one's really important. Both samples have to contain at least 10 individuals in each category, all right, for this to be a valid test. And so that is, they satisfy these mathematical equations I've got down here. You take the sample size from the first group, I'm looking right down here, N1, and multiply it times the proportion of it. That needs to be greater than or equal to 10. So you need to have 10 people that represent, your overall proportion in group 1. And also, if you take N1 and multiply it times Q1, which remember Q1 is that P1 minus 1 value down here, it also has to be greater than 10. That's just for your first group. All right. The same thing has to happen for your second sample as well, or your second group. So your sample size of your second group times its P2 probability or proportion has to be greater than or equal to 10, and so does the sample times the Q2. In other words, Q2 is just P2 minus 1, also times 10. All right. I don't need you to memorize this, but this is a check. This is kind of a checkpoint. I may ask something about this in the quiz. I may ask you to check, give you a sample and some breakdowns, and ask you to check that in the quiz to see if it would be okay for us to go forth with this kind of test. Okay. So when we do this by hand, and I'm going to do one of these by hand, the confidence interval today, but I don't expect you to memorize all these formulas, as I usually say. All right, so if you're doing either a two proportions confidence interval or test, all the following hold true. The target parameter we're shooting for is the population proportion of group 1 minus group 2. All right, P1 minus P2. Remember, P without the hat on it represents the population proportion. But to get that, since we're taking two samples, to estimate what that target parameter really is, we're going to use the sample means. So again, this guy, P1, P2, usually equals out to 0 because we're going to assume they're the same when we start any of these tests. And so that's really just something statisticians throw in here in the formula because we need to have that represented somewhere. But usually we don't worry about that. We worry specifically about the estimator. All right, P hat 1 minus P hat 2. So, and P hat 1 is just whatever the number of people are, say we'll call it X1 from group 1 that fit your criteria, divided by the entire sample size of group 1, and your P hat 2 is equal to the number of people that fit the criteria in the second sample divided by its sample size. So that's really what we're going for with each one of those. Okay. The standard error is what we call a pooled standard error here, and it's what they use predominantly in most textbooks. And it's this value called just P hat. Notice there's no subscript with it like there was up here in the estimator. And they do 1 minus the P hat, and then they do 1 over the sample size of the first group plus 1 over the sample size of the second group. And that P hat value is found by using this formula down here. It's taken and basically getting an average of basically adding the two X values together, or totals together, divided by the total of both sample sizes added together, and kind of gives you like an average, if you will. It's not really a true average, but it's kind of an average between the two proportions, and you use that for your standard error. All right. So it's kind of there's a lot of different little sub formulas with this thing that can be a little bit of a pain. We do use the normal distribution in this case. When we do it in R, it will be different. All right. I'll explain that in a minute. R uses the chi-squared distribution instead, because as we saw when we ran the prop.test function before, we got a chi-squared test statistic instead of a z-test statistic. And what we'll find out is that the values we get when we do this by hand are not very different from what the chi-squared give us, and so they're very similar in nature of what the outcome comes out to be. And so it really doesn't matter which one we use, but we're going to pretty much use the R version for you guys. All right, and it's quite okay, but I'll show you how close we are between the two after we do this one by hand. All right, so bear with me. So to do the confidence interval by hand, which is the one we will do by hand, we have to decide on our confidence level. You as the researcher, in this course I'm going to tell you, like I always do, find me this confidence interval, but in real life you get to determine the size of your confidence interval. Most people, if I haven't said this before, pick somewhere between 90% to 99%, and with a majority of folks sticking with 95. All right, that's kind of like the status quo, if you will. Most people pick a 95% confidence interval, but it's your choice as the researcher. Okay, I won't stick into that world, but here we go. There's my p-hat1 formula. That's what we'd have to obtain the values for that. We need n1, n2, the sample sizes for each sample. We need the proportion, so we need the x1 value and the x2 value, the number of people that fit the description of what we're looking for or what our research is about from each sample, and we get our p-hat values from those using these formulas. And then we also need that the regular p-hat value for the standard error calculation we have to do, all right, where we add them together. So we need those items. We also need to calculate our critical value. Remember, that's what we call z sub alpha over 2 when we do a z distribution or a normal distribution, and we can find that by doing q norm of alpha divided by 2 comma lower tail equals false. All right, so it's pretty simple. Once we know what our confidence level is, our alpha over 2 is just this value right here. It's 1 minus the confidence level divided by 2. All right, so we'll do this in piece in a minute, and then we have to use this big formula here. Whatever our confidence interval is, we take this is our point estimate here. We call that the point estimate. The p-hat1 minus the p-hat2. That's the center of our confidence interval. It's the centering point. And then we add or subtract to that to get our endpoints, the critical value times the standard error. This is that pooled standard error. Okay. And then, of course, interpretation of these intervals are very similar to our 2-sample t-intervals, so you can use that cheat sheet for these as well, except for instead of you referencing the mean here, you reference the population proportion rather than the mean, because, you know, we're dealing with proportions instead of means here, so we want to keep that in mind. Okay. Now if we run the z-test, or the 2-prop z-test here, the only thing we need really is the test statistic for the proportions, and we get it by doing this formula here. I'm not going to stick on this page so too drastically, but you can read through it. We need the basic same things that we needed when we ran the confidence interval up here, but then to get the z-test statistic, we need this, and then this stuff down below here. Once you've calculated the z-stat, you can come down here and look and say if you're testing, and notice my confidence, how I've written my ho and my ha here. I'm using p1 equals p2. p1 is not equal to p2 if I'm doing a 2-sided test. That's what this first one represents. If I'm doing that, I want to find the p-value for my z-stat that I just calculated in the yellow box. Then I do this formula here in R, 2 times p norm times whatever the absolute value of t-stat is, comma lower dot tail equals false, will give me the value for that. And the reason I do 2 times is because I'm doing it's twice the probability in this case, because we're talking about 2 sides of the 2 tails on this test. All right, when you do a 2-sided, you got 2 tails. If you're testing a 1-sided test, like for example this one here, the second bullet down here, if testing P1 is greater than or equal to P2 versus the alternative, which is what we're usually claiming here, the proportion 1 is less than proportion 2, so we're doing a less than test, then we run just a P norm on the z-stat itself. All right. that's going to give us the less than value, and that z-stat will mostly likely be a negative value in this case. Okay, if we're doing a greater than one-sided test, so if we're doing this here, P1 greater than P2, then we use the same p-norm function, but inside we'd put the z-stat value we got in the yellow box, and then let lower.tail equals false, because we want to go to the we want a probability of the upper end of the tail, if you will, or if you're looking at the normal curve, the right side of the curve. All right, so we want probability going from that z-stat up. Think about it this way. So I know sometimes I don't draw enough pictures, but if your z-stat was here, then what this function right here is going to do, what this last function right here is going to do, is find you the area underneath the curve to the right. The one that I did in the second bullet right here would be area to the left, and so most likely your thing would look kind of like this. Your z-stat would be down here somewhere, and you'd be finding area down here. In that very first one, just kind of draw you a little picture here. It's a two-sided test, and so what that p-norm function does is it says, hey, I know you've got a z-value down, you're going to have to think about two sides here. There's a negative z and a positive z, so whatever this value that the yellow box, the formula in the yellow box spits out, that z-stat, it's going to be either negative or positive depending on the outcome here. And it could be either one, but if we're doing a two-sided test, that multiplying by 2 says if the value is positive, I'm going to find the area here, but I'm going to multiply it by 2 because I also need the area down here. All right, so that's what that does. All right, again, I'm not going to make you guys do this one by hand. We're going to let R do the work for us on that. So, like we've seen the function before for the R function that works for us. For the 2-prop interval, we're going to use the prop.test function in R. All right, so we've already used it before for a one sample proportion that we were looking at. Now we're going to look at it too. So it has all the same inputs in it. So the difference between what we did before and what we're going to do now is we have to find a way to get two samples in it, two x values and two y values, because you remember before when we had one sample, we only had to put, like say we had 70 out of 500 people, say x was 70 and n represented 500, and we had 70 out of 500 people with our one sample, then we would put 70 in for x, 500 in for n, and then we'd list out anything else we needed in this case. Okay. If we were doing the prop.test for our two samples, in other words, we're going to have an x1 and an x2, so maybe we have a separate sample n1 and n2. So n2 could be, say, maybe 620 people. We had 90 of them over here. All right, so then in that case we would have to put in a little vector inside prop.test the x1 and the x2 first, comma, and then the n1 and n2 second. I'm going to do an example of this shortly so you'll be able to see it. Okay, we'll do it together. All right, so let's do an example of a confidence interval specifically, and we'll do this one by hand. So biofeedback is a treatment technique in which people are trained to improve their health by using signals from their own bodies. So specialists in many different fields use biofeedback to help their patients cope with the pain. Okay. A study was conducted to compare a biofeedback treatment for chronic pain with an NSAID, what they call a non-steroidal anti-inflammatory drug medical treatment, so some kind of NSAID medical treatment. A group of 2,000 newly diagnosed chronic patients were randomly assigned to receive one of the two treatments. All right. After 6 weeks of treatments, the pain level of the patients was assessed. Of the 1,000, so here are two different samples, who were on the biofeedback treatment, 560 of them said they had experienced a significant reduction in pain. And of the 1,000 patients who had taken the NSAID treatment, 680 of those said that they had experienced a significant reduction in pain. Okay. We want to construct a 95% confidence interval on the difference in the two proportions. All right, so that's what we're trying to do here. So what should we pull from this? What's important to us? Well, we know the biofeedback treatment. We could call that P sub B if we want to, so we know it's biofeedback. We've got X1 or X for the bio if you want. We'll just call it P1. X1 over N1 in this case will be 560 is our X1 and 1000 is our N1. And for the second group, the NSAD group, X2 over N2 in this case will be 680 over 1000. All right, and we're going to list these on the next page as well, so we'll pull those things over to help us out on the next page. So I've got my X1 is 560, X2 is 680, and my N1 and N2 are actually equivalent, but they're both 1000 each, and we know we want to make a 95% confidence interval in this case. So we need to construct P hat 1, P hat 2, and that P hat value. Now this is just X1 over N1, so that's 560 over 1000, which really equals 0.56. Okay. And we got P hat 2, which is 680 over 1000. All right, which is just X2 over N2, which is equal to 0.68. And then we need to do the P hat 1, which is X1 plus X2 over N1 plus N2. And so if we take our X1 560 plus 680 divided by 1000 plus 1000, all right, and add the top first and then the bottom before you divide, for those of you who forgot your orders of operations. In this case we should get 0.62. That actually, in this case, because our sample sizes were even, came out to be the exact midpoint between P hat 1 and P hat 2. All right, so we've got those values that we need to use in further calculations. All right, so the first one we need to do is P hat 1 minus P hat 2. So we got 0.56 minus 0.68. And this is going to give us our point estimate, okay? The center of our interval. And that comes out to be negative 0.12. And then we need to calculate our critical value. So in here, we're going to do Q norm. 1 minus I use this formula just straight up. I just go ahead and put 1 minus the confidence level, which is 0.95, divided by 2, and then put lower dot tail equals false. Now pay attention that I put those parentheses around the 1 minus 0.95. If you don't do that, R will give you an incorrect critical value. So we're going to do this. 1 minus 0.95. Actually, sorry, let's call the Q norm function first. Q norm. Yep. Open a parenthesis, 1 minus 0.95. Get out of that first set of parentheses, divided by 2, comma, lower dot tail equals false. And what do we get? We get 1 point. We get let's see here. Let's come back over here. We get 1.959964. Or you could really round this to 1.96, but we're going to be accurate as we can be with this, since technology allows us to do so. So 1.959964. All right, so we've got that. All right, so we're about to go on to the next page, and we still need the information from this page. So we got this guy here is going to be our point estimate. We've got our critical value. The next thing we need to calculate is going to be our standard error, which is using that p hat value, which is 0.62. So we're going to need this in the next step. And we're going to need the remember that the sample sizes are 1000 each. And so to calculate this, we're going to just do square root of 0.62 times 1 minus 0.62 times 1 over 1,000 plus 1 over 1,000. All right, throw that in your calculator. We're not going to calculate that out. I'll just give you the answer here. The sigma sub p hat here is 0.02170714. So make sure you get that, because that's a value we need. So now we have everything we need. We just need to plug it into our formula for the confidence interval. Remember, the p hat 1 minus p hat 2 on the previous page was negative 0.12. So we got negative 0.12 plus or minus the critical value was that 1.95. Let's see, where was I at there? 1.959964 times the value we just got up here for our critical value, or for our standard error, which is 0.02170714. All right. So when I take each one of those negative 0.12 and add the value that this comes out to be here, and subtract that value from the negative 0.12, I get two different values. And the lower bound that I get, or this is the interval I end up getting. I get lower bound is negative 0.162 5452. And the upper bound I get is negative 0.07745 All right, I know I went ahead and took it all the way out to what we would get. We don't need that many decimal places in our interpretation, but since they're both negative, that tells me that proportion 2, all right, the folks on the NSAID treatment had a higher had higher levels than the first one. So very similar to what we did with our two samples. When we get two negatives, we know the second proportion or second mean is greater than the first. And so we would say we are 95% confident that the population proportion for the patients on the NSAID treatment were at least the NSAID treatment who experienced, you can be more specific with this, and I have in my other notes, so you can look at that, but who experienced a significant reduction in pain level. And I'm not going to write that out here, but that's in the notes, my R code notes, so you can find it there. Were at least .08. I'm getting that from rounding this guy here. 0.08, and at most 0.16 higher than the patients who were on the biofeedback treatment. Be glad I don't write everything out all the time. All right. I have terrible handwriting, and I know it. But yeah, so that's it. That's why we interpret it. So before we move into another example of doing the hypothesis test, let's throw this into R. We're using the prop dot test to see what we get. Okay. I didn't make a slide for this because we basically interpreted and done everything we need to do. But if we wanted to run this without doing much in R, we just need to do the following. You need to do prop.test, all right? within it, we need to put both x values, x1 and x2, in that order. All right, so remember, for the biofeedback treatment group, x1 was 560, and the NSAID group folks were 680. So that's the first. That just gives our x values. Now we put another comma, so we put our x values in. Now we have to put a vector of our sample sizes in. So they were both 1,000, and unfortunately you can't put it in once, you got to put it in twice. 1,000, 1,000. I'm going to put this command in here that says correct equals false. This is what they call a continuity correction, and if it's set to true, your outcome will be a lot different than what we got, or be a little bit more different than what we got when we just did this by hand. But I recommend you always use correct equals false, because it makes your outcomes or your output for your interval values closer to the one we did by hand. All right, so because we're going to get it like I said, this particular function uses the chi-squared distribution rather than the normal distribution. And so we see here when we get our output, the chi-squared, we got a chi-squared test stat value, which tells me that it's using the chi-squared distribution, and it's also doing the same thing for the interval. But we get very similar results. This value right here on the lower side is negative 0.1622. That starts to differ right there around that fourth decimal, which is not a big deal, right? So we still round that to 0.16 if we ignore the negative sign. Here's the same thing. The upper side for the interval we got was 0.07745. 0.7745. This is 0.7778. So it starts to differ around here too, but it will still, if we round it off to 2 decimal places, we're going to round to 0.08. So you can see these are very similar results. So we're going to use this method here going forward. You don't ever have to do this one by hand, unless you just really want to. But I don't think many people are going to want to. But again, read these very similar to what we did with the 2 sample intervals. All right, it'll be very similar. Okay. All right, so we're going to do the next example strictly in R. So we're going to do a hypothesis test in this case. So I've got medical researchers performed a comparison of 2 drugs, something called clopidogrel and ticagrelor, or something like that. Who knows how they pronounce these drug names, which are designed to reduce the risk of heart attack or stroke in coronary patients. All right, so they got these 2 different drugs. A total of 6,676 patients were given clopidogrel, and 6,732 of them were given ticagrelor. I don't know. I'm having fun with this now. But so we basically have the sample sizes of how many people took those. Of the clopidogrel patients, I get tongue-tied when I try to say that one, 668 suffered a heart attack. So there's our X1, if you will, and suffered a heart attack or stroke within 1 year. And the folks that took the Tika drug, were 569 of those folks, and so there's our X2. So we've got that information. We know X1 equals 668, X2 equals 569, because those are the 2 things we're interested in, are the qualifiers. You know, we wanted to know how many people suffered on a heart attack after taking these drugs. And N1 6,676, because that's the clopidogrel patients. And then N2 should be 6,732. So that's the only information we really need from this to do our test. But the conclusion they want us to come to is down here. Can we conclude that the proportion of patients suffering a heart attack or stroke is less for the folks on the Tika drug? All right. So that's what they're wanting us to try to discern here. So in R, before we did R, we want to state our hypotheses. So the notation for this is using lowercase p with subscript. You can use just 1 and 2 if you want to you do that. I used the C and the T to represent the two drug names. And remember, what we wanted to see if we could conclude whether the patients on the TICA drug were less than those on the clopidogrel drug. And so I did clopidogrel greater than PT. You could do this reversed as well. You could put these reversed. You could actually do this also. PT is less than PC, and you'll get the same results if you put them in that order, but you just have to reorganize the way you put your data into R. So if we want to go, if we call X1 the clopidogrel group and X2 and N2 the TICA group, then we have to put them in that order. So since I called, this is really X of C, if we will, and this is X of T. This is N sub C, N sub T. So we have to keep that in mind if you want to think of it that way, to kind of keep track of it. All right. So just like I did before, I'm going to run my prop.test to get my test statistic and my p-value for it. And we're going to do an alternative greater than in my case, because I did the C group before the T group, so they have to be greater than the TICA group to show that the TICA group is less than. All right. So over here, let's just run it over here real quick, just for good measure. Prop.test. I'm going to have C. The first, we take 668 was the clopidogrel group, or whatever they're called, and then 569 was the TICA group. That's my two X values from that. My two sample sizes from those groups were the 6676 for the C group and 6732 for the TICA group. And then I need to do alternate, or whatever they, yeah, there we go. Alternative equals greater. Make sure you put that in quotes. And then correct equals false. We don't want the correction. We want to keep it as false. And it gives me a p-value of really small one, 0.009399. So that's definitely something we're going to reject. The null hypothesis, which stated they were equal, or that the clopidogrel was actually less or equal to. Okay, so we're going to reject that and say that clopidogrel definitely caused more heart attacks and strokes in the first year, and the TICA group was better. It did less. All right, so that's what we're finding out here. If we had ran that in the reverse way, just for your purposes, we should have gotten the same results. So say if I reverse these around, I just want to show you that it didn't, as long as we keep the correct things in order here. So that was 668, and over here I need to take 6676, take that away and put it behind the other one so that they're in the reverse order for each one. And I ran a less than test instead. If I did less here, notice my p-value came out to be exact the same. So the order you put them in doesn't really matter as long as you pay attention to what you're trying to find. All right, so you could have done a greater than or less than test here. You should get the same results. All right, if you ever get an insanely big p-value, like 0.99 something, you did something wrong. I can just tell you that straight off the bat. I've very rarely seen, it's a very rare occurrence that you should ever get a p-value of 0.8 or higher in these cases, all right, with these types of two-sample testing. Just not seen very often. So that means you usually put things in the reverse order from what you meant to do. So be careful with that. I would say put them in the order you find them in the problems, and then look at what the question's asking. Okay, well, which group they want to be less than, and put the, as they, like we teach in elementary school, put the alligator eating the proper P symbol. All right. So what would we conclude here? Our conclusion, since our p-value is definitely less than 0.001, we reject the hoe. There is very strong evidence that the true population proportion of patients suffering a heart attack or stroke is less for patients who take the drug Tika than those who take the drug Clop. Let's call that Clop. Clopidogrel. All right. So that's the hypothesis test. We wanted to do a confidence interval for this particular one. We'd have to go take the alternative equals greater out of the equation, so we get a two-sided confidence interval. Okay. Now I noticed there is a 1 here, but remember, confidence intervals are always the two. You have to set this to two-sided instead of greater, or just leave the alternative argument out completely, and it will do a two-sided test automatically. It's default to do that. All right. So when you want a confidence interval, just leave that argument out altogether. All right, let's talk about the chi-square goodness of fit test, because I feel like I'm going to run out of time here in a minute. The chi-square goodness of fit test is applied when we have one categorical variable from a single population, and we wish or determine we want to determine whether or not the sample of the data that we have fits to what they call a hypothesized distribution. In other words, there's already proportions set out for a specific distribution, and it's already known. And we went out and collected data on that, and we want to see how well our data fits to what the hypothesized distribution that's given to us states. All right. This test is very similar to our two proportion test we did, but we can use this to check if two or more proportions fit to a specific distribution. So we don't have to limit it to just two. We can like check out several of them at one time. All right, because there may be more than one scenario or more than two proportions in a group. The chi-square goodness of fit test is okay to use when the following conditions are met. We have to meet these. These are our assumptions for the chi-square goodness of fit test. As usual, we have to have a simple random sample. That's always going to be true of every assumption that we make for any test. The variable under study is categorical. All right, it has to be categorical. And the third one is really the most important one. The expected values for each level, we'll talk about what expected values are in a minute, for each level of the variable is at least 5. All right, so we'll calculate these things called expected values, the values we expect to see based off of the proportions and the sample size we took. If any of those are less than 5, this test is not going to be very good for us. Sometimes they'll tell you that you can have at most one of them be less than 5, or there's another criteria we'll see when we talk about the other two types of tests. But nonetheless, this is what we want to check. I like to say just look to see if there are any less than 5. If they're less than 5, then we're going to have some issues. All right, I'll show you what I mean here shortly. That may not make sense yet. All right, so when we perform a chi-square goodness of fit test, we do the following. We assume the following hypotheses for your categorical data. So the null hypothesis is going to be just a restatement of what the theoretical probabilities that are either given to us or something that we can find using a distribution. All right, so we'll call them P sub I. It could be P1, P2, P3, or if they've got specific names to the groups, we could call them P sub whatever our symbol we want. But then they equal the proportions for those things, all right? And those are usually given. The HA is always going to be this. At least one of the cell probabilities, or at least one of the probabilities, differs from the hypothesized value. All right, we can be a little more specific when we have something to go off of, but that's usually the way. The HA is just a worded thing in this case. We're saying at least one of those things differs from what we know. All right, so the values in your cells, well, we're going to build little tables, that's what I'm referring to as cells here, are called observed values. So we go out, we collect data, our observations, and we get counts. So we might, and the one we're about to do is based off of flowers and the different colors of a specific type of flower found in a field. So we went and we took a random sample of flowers and we kept account of the colors that we had in there, and that's what we're going to use as our observed values, what we actually observe in the field. So we need to compute the expected values for each of those using the theoretical probabilities that we know about the types of colorations of this flower and our observed and our total sample size. So each each of the expected values for each cell is going to be equal to this little formula here. We take the total sample size n and multiply it times just the probability for that specific type, in this case flower color, or specific condition that we're looking at. All right, so each one will have a different probability. And then we need to check to make sure that each expected value is greater than 5. Well, once we calculate it, that's easy to do. All right, so there's our assumption check that we have to do. To compute the test statistic by hand, the chi-square test statistic, we have to take and sum up for each cell in our table that we have to do this for. We take the observed value minus the expected value. So people might write this observed minus expected. We square that value and we divide it by the expected value of that particular cell. So we take the observed from the cell that we're looking at in the table minus the expected, square it, and divide it by its original expected. We get that for each cell in the table, and then we add them all together. All right, so that's why I said you sum them up. To get the p-value for the chi-square distribution in R by hand, and don't worry, I'm not going to force you to do this by hand, but I'm going to offer you something here in a few minutes. But the p-value is found using the p chi-squared function, and we throw in our chi-squared value. We have this value called k minus 1. It's usually the number of cells we have in our table that we're looking at minus 1, all right, or the number of proportions we have minus 1. And then we set lower dot tail equals to false, all right, and k minus 1 acts as our degrees of freedom in this case. So like the t distribution, the chi-square distribution also has degrees of freedom, so we have to keep that in mind. Okay, so we're going to do one of these by hand, but I'm not going to force you to do these by hand. There's a quicker way in the calculator, of course, in R, as there always is. Okay, so in Snapdragons, the Mendelian genetic theory states that the offspring of two pink hybrid parents, flowers, should produce offspring of k equals 3 different types. All right, so I'm letting you know what k is in this case. Independently at the following rates. The probability that the offspring produced is red is 0.25. So there's one of the theoretical probabilities I'm talking about. The probability of getting a pink one is 0.5, and the probability of getting a white flower, or snapdragon in this case, is 0.25. Suppose a random sample of 234 snapdragons showed the counts in the table below. Is this strong evidence against the Mendelian theory in this setting? So did we find an obscure result? So that's what this test is really looking at. Did we find some obscure result in nature that goes against what the genetic theory states? The total here is just columns. I want you guys to get used to ignoring. You don't need that, but we do need these first 3 cells. Okay, so let's kind of get into this a little bit and do one of these by hand, and we'll play with the formulas a little bit. So the null hypothesis here are just going to be us restating those probabilities we saw on the previous in the problem. So probability of red, so we could see p of red is equal to 0.25, comma, piece of pink is equal to I think it was 5. Is that correct? Yes, and then the probability of a white flower is equal to 0.25 as well. The alternative hypothesis in this case is going to be at least one of the probabilities differs from the Mendelian genetic theory, or Mendelian genetic theory. You biology people might know how to pronounce that better than I do. All right, so that's it. So now we have to calculate the expected values of each one of these. So again, ignoring this total row, we don't need anything here, but we do need them in the remaining 3 cells. So we know the total is 234 overall. That's our n. So notice the n. So this is going to be, so define the expected value of the reds in this case. We take 234 and multiply it times the p-value that we were given in our hoe, which is 0.25 for the red. So I'm using that value right there. Okay. And when I do that, this is going to equal the expected value outcome for this case is going to be 58.5. Well, that one's bigger than 5, so we're good to go. Assumptions so far so good. The expected value for the pink flowers is going to be 234, the total again, in here, okay, times the probability of it, which was 0.5, so we're taking half of 243, or yeah, half of 234, not 43. And that's going to give me, I think, 117. All right, so far so good on the expected values. And then for the white, expected value of the white, we take the 234 again and multiply it by the pink value, probability value up here of 0.25. All right, so 0.25 there, and that should come out to be the same as our first one, which is 58.5. So our expected values all check off that assumption. We're happy with it. We might write something not for a publication, but for our purposes for this class, we might say, hey, all the expected values are greater than 5. The assumption has been met. We can continue on with the test. All right, but we need to calculate the test statistic now that we know that our expected values are all good. So I'm going to put a check mark next to that. So to find the expected values, remember this is the observed value minus the expected value of the group divided by the expected value. All right, and we got to square that as well. So the first entry is going to be 54 minus 58.5. We're going to square that, but divide it by 58.5. All right, then we're going to add to that the expected value, the observed value from the pink, which is 122, minus its expected value, which is 117. Square that and divide it by 117. You gotta be very careful when you're putting these numbers in by hand. This is kind of why you don't want to do these by hand, because if you have more than 3 categories here, it gets tedious. And then the last one's going to be our observed value was 58 minus 58.5. We square that booger and we divide it by 58.5. All right, so by its expected value. All right, when you multiply those together and then add them all up and do the square the tops, divide by the bottoms, and then add them all together, what you end up getting is the following: 0.5614, 0.5641. Sorry. So there's our chi-square test statistic. Now we're going to need that to figure out the p-value. So the p-value is just literally, we're going to write in p chi-square, and we're going to do this in R. And that's the 0.5641 is our first input, the chi-square value we just calculated. K minus 1 is 3 minus 1 in this case, because remember k equaled 3, so we just plug in 2 here, and then lower dot tail equals false, which equals 0.7542. All right, that is way bigger than 0.10. It's not bigger than that 0.8 I mentioned ago. This test is a little different than the 2 sample testing, and it's rare to get a p-value this high. And with categorical table tests like this, like the chi-square goodness of fit test and the ones we'll do later, getting a high p-value is actually sometimes seen as a good thing, depending on what you're looking for. All right, so we write our conclusion, and we would conclude the following: since p is greater than 0.10, we do not reject hoe. All right, the Snapdragon counts that were obtained, or observed, if you will, that were obtained appear to follow that Mendelian genetic theory. Boom. So, I mean, maybe you didn't, depending on what you're trying to do, maybe you wanted it to reject, but in this case it did not. We didn't find a sample of flowers that debunked the genetic theory. So that's how you do it by hand. Let's run it, show you how to run it in R real quick. All right, so to get the chi-square test to run in R, we use the chi-square.test function. That is already built into R. You don't need any special package installed or anything like that. This is part of the base package. So we'll need to input our observed values in one vector, all right, as a vector, and the probabilities we have, we need to enter those in as a vector as well. Just a quick note here, I will always probably give you the theoretical probabilities so you don't have to go do a bunch of extra work to get them. But there are times when the theorized probabilities might follow a distribution that we've seen in the past, like the normal distribution, the Poisson distribution, any other those distributions. Our probabilities might follow a specific type of distribution, and we may have to figure those out prior to doing the test. That doesn't always happen, but it does in real life. That may happen from time to time. Okay. And there would be a reason for you to think that, maybe from previous research that's been done in the area you're looking into and whatnot. But oftentimes you're going with some theory that's already out there, some observations and probabilities someone else has come up with from a test they've done prior. All right, so I'm going to run this in R real quick. Chi-square.test function. Notice I put my vector of observed values in first, and then P equals a little vector of the probabilities. Now, we checked the expected values of these observed values by hand when we did this by hand a minute ago. R will do that for you too. You just run the chi-squared test function, but at the very end of it, after you close your parenthesis off, you use the money symbol and you put a lowercase expected in there, and it will give you those observed values that we found when we did it by hand. So this usually should be done first, and then this done second. All right, and we will do that in the last example here. As a matter of fact, I won't plug this in right now. You see what the outcomes are here. The chi-square value came out to be exactly what we calculated when we did it by hand, and the p-value, when we used R to calculate the p-value using the p chi-square, that's the value we got there as well. I don't have it on here anymore because I had to fix something on the slides, but those are the values we got when we ran it by hand. So one quick note, I'll always require that if I ask you to do one of the chi-square tests we talk about, we're going to talk about 3 specific ones today. This one's the first real one we're talking about, goodness of fit test, and I'm talking about chi-square test on categorical data, not like the standard deviation one we did a few lectures back. But the chi-square goodness of fit test and the 2 we run in the next lecture, you can just use this chi-square.test function for the most part in all of those. I won't require you to do these by hand, but I will go ahead and tell you right now, if you do one by hand and show me all the steps like I did with you in the recording, I will give you 5 bonus points to use either here or on a quiz or something where you wanted extra 5 points on to help your grade out. So it's extra credit if you want it. If you don't want it, then just do the chi-square test. But to get the extra credit, you have to show me the steps in the work. You can't just say this equals that without showing me the steps that got you there. All right. So let's do this last example for the chi-square goodness of fit. We've got a laboratory that's comparing a test drug to a standard drug. preparation, all right? So some way they prepare the drug, and so they got a test drug they're trying to improve upon something here. And it's useful in the maintenance of patients suffering from high blood pressure, all right, these drugs that they're working on. So the test drug they're probably hoping is better in some way or another. The standard drug's probably pretty good, but they're hoping their new drug's better. So from that previous standard drug, this is what's known. From the previous study, and it was a large one at that, the standard percentages are as follows. 50% should show a marked decrease, or in that study they did show a marked decrease in blood pressure. 25% of the participants should have a moderate decrease, and 10% should have a slight decrease in blood pressure, and 15% of them would show a slight increase in blood pressure. So the lab went off and conducted a clinical trial with a random sample of 200 patients with their test drug. Right? All the patients were required to be listed according to the same hypertensive categories that the standard drug classifications were. In the way this words it is the categories of the NYHA, which I assume stands for New York Health Association classifications, under that standard prep. The results on the next slide of this study of the 200 people test the hypothesis that the cell probabilities associated with the test preparation of our test drug on the next slide here is identical to those for the standard trial, the probabilities. So we're going to use these probabilities and these descriptions for the categories for our new study as well. But we're going to see if our observations from our 200 patients match those of the previous drug. All right. So that data looked like this. The marked decrease here, what I call a MAD, was 120 people showed a marked decrease in blood pressure. 60 people showed a moderate decrease in blood pressure. 10 showed a slight decrease, and another 10 of the 200 folks showed a slight increase. So far this drug looks pretty good to me. But we need to test to see if it's any different from the other drug. And so what we're going to do here is we're going to make our we're going to do what our step one is usually in this course, is state the null and alternative hypothesis. And so the hoe here is just me listing those probabilities for each of the categories that were given to us, the theoretical probabilities. So I've got the probability of a marked decrease is 50 or 0.5. Moderate decrease is 0.25. The standard or slight decrease was a probability of 0.10, and the probability of slight increase was 0.15. And the alternative hypothesis is going to be at least one of the probabilities differs from the hypothesized value for the standard preparation. All right, because if they differ, then maybe we have something good with our drug, right? That'd be a good thing. So to calculate the expected values, we have to get the data in the table as a vector here. All right, so from here to here. We don't care about the total in this case, because R will do that for us. But we need to check the expected values to make sure that they're good. So I'm going to go ahead and call the chi-square.test. And we're going to go ahead and set everything up real quick. So our first vector are the observed values, which is 120. I'm going to put them in the order we saw them in the table in. 60, 10, comma, 10. All right, we're going to get out of that set of parentheses or that vector, comma, and we're going to do P equals C. Make another vector of the probabilities in the order they appear because they match the order of our table. So it should be 0.5, comma, 0.25, comma, 0.10 or 0.1, and then comma 0.15. All right, and then after that I'm going to put the money symbol expected, because before we run the test we should make sure that we should even be running this test. And it shows me that the expected values were 100, 50, 20, and 30. And so those are all greater than 5, so we're good to go. So the assumption, remember, was that we must check the expected values to see if they were 5 or greater in order to proceed with our chi-square goodness of fit tests. So we see that here. We're good to go. We've checked our assumption, we feel comfortable, we're moving forward. Step 3 is we just actually run that chi-square test, and basically in R, all I would do to get that is, since I've already run the expected value version, just push up on the arrow key once and erase the expected value, the expected wording, the word expected and the money symbol. Run it again. We get a very small p-value, which means we're going to reject the null hypothesis. So that 2.128 e negative 5 is really equal to, let's see, 2128 1 2 3 4 zeros, I think. Yeah. Yep. Double checking myself. That's a really small p-value. That's what that actually turns into. So we're definitely rejecting the null hypothesis. We're going to go with the ha. There's definitely something different. At least one of the probabilities is different. So conclusion would be, since p is less than 0.001, we reject the ho. At least one of the cell probabilities is different from the hypothesized value given to us in the standard preparation. And actually, if you think about it, if we look at the values that were our observed values versus the expected values, we kind of see a difference, because remember the expected values were 100, 50, I believe 20 and 30. Yeah, 50, 20 and 30. This is a lot less here. This is a little bit less here. This is a little bit larger here, which is good, because that was a moderate decrease, and 120 is a marked decrease, so there were 20 more people there. So we had more people in the groups where it was showing more decrease in blood pressure. There were a few less in the slight decrease, and there were less, quite a bit less. 20 is a differential of 20 is a pretty big deal when you're talking about a slight increase. So this drug, it looks like you could actually almost say that it appears that our drug may, you don't want to say it definitely does, may have may be better at decreasing high blood pressure. That's something you could tag on to the end of your conclusion. So I'll quit going on about that. We're done with this. Talk to you guys in the next lecture about a couple more chi-square tests, and I hope everybody's doing well. Take care, everybody.